it will take almost like 5 minutes to unwind this. See, this has to unwind 100%. The reason why that tape maybe is just less than 1 gram, but it doesn't matter, it has a mass, and because this is causing a lot of torque on this thread, now it has to rewind. So in other words, now it's going clockwise. This part of my experiment has to do with conservation of angular momentum, and then I thought if a planetary level, when we have a nebula that's forming a planet, the nebula is like a huge disk. When it gets contracted and the rotation increases. So in other words, the inertial mass or inertial rotation becomes inertial speed. So this is exactly 14.5 gram, and then I divided it in 6 pieces, but you can tell the axis of rotation here is exactly 6 inches on each side, but this one is only 1 inch. But it's exactly the same mass and both of them are suspended. If I let this go, it's going to go counterclockwise, and the important thing is this is following this moment of inertia rule, which is I, is always mr2 or mr squared. The reason why, the more mass is spread from the axis of rotation, it's the slower it goes. When it gets closer like this, it's going faster. Now let this go. You can tell I put a planer underneath. This will take 28 seconds for one rotation. See how small it goes, how slow that goes. I have to be careful. Okay. See how slow that goes? It takes exactly 28 seconds, but this one is exactly the same mass, 14.5, because it's close to the axis of rotation. You can tell this one goes only 5 seconds. Look. Did you see how fast that one goes? Okay. This has to do with conservation of angular momentum. And this is 516 rod, and it's exactly 118 grams. But what I did this time, I have 50 grams. Each one of these washers are 50 grams. So if I have this all the way to the end, to the tips or on both ends, it will take exactly 40 seconds. As I move this closer to the center, exactly where they are just touching this thread, that'll be only 22 seconds. So this proves that even in a smaller scale like this, the conservation of angular momentum works. So I'll let this go. First, when I put this 250 grams on the side, you can tell how slow that goes. Due to the moment of inertia, and like I said, they are far from the axis of the rotation. You can tell. This will take 40 seconds. I have to adjust this a little bit. Yeah, it will take 40 seconds, one rotation. You see how slow that goes? But see now, as I move this toward the center or axis of the rotation, is going to pick up speed. So in other words, the rotational inertia increases and rotational speed increases. See now, the mass is concentrated at the axis of rotation. Well, of course, we have still more mass over here, but this one is going to go 22 seconds. See, but something important happened here. It's very difficult. First moment or first few seconds, it has to overcome the inertia. And then it picks up speed, exactly like I explained, like the falling balls. Well, of course, this is not that fast, but it's the same concept. Always gain the momentum. If I let this go like 5 minutes, it might even rotate like 5 seconds or even less than 5 seconds because of kinetic energy, and that makes it more complicated. Well, of course, I don't want to explain the kinetic energy now, but the kinetic energy comes in equation immediately. This is another experiment for conservation of the angular momentum. The first one is 12 inches, and that's exactly 90 grams, and the second one is 180 grams, and the third one is 270 grams. And in fact, the first rotation takes 25 seconds, and the 24 inches, which is 180 grams, takes 75 seconds, and the big one over there, I'll show you in a minute, that's 36, that takes exactly 90 seconds. But when I combine them all together, it takes only 40 seconds. So this shows how far the distribution of mass is from the axis of the rotation. This is the 12 inches. And then of course I put some plates, you can tell. See, this one is 24 inches, but you can tell it's going to rotate slowly, very slow, compared to the other one. Of course, it's very difficult to adjust and balance them because force of gravity is exactly the same on both sides. It must be milligram. See how slow that goes? That's 24 inches. The reason why, that has twice as mass. But you see the distribution? It's almost 12 inches on each side, but that one, the small one, is only 5 inches. But as you can tell, as the time go by, because of kinetic energy, they pick up the angular momentum, or they pick up angular acceleration. And the other one, and this one, is 36. You can tell how slow that one goes. And then if you compare to the big one, to the small one, you see how fast the small one goes. Well, of course, I don't want to waste a lot of time. And like I said, if I take them together, entire thing is going to be only 40 seconds. This is another experiment for conservation of angular momentum. I made my own gearbox, but you can tell this is 24 inches rod, and it's exactly 472 grams. And when I torque this, you see I don't need any force whatsoever. See how easy that goes? Because the axis of rotation, you can tell, everything is contracted to the axis of rotation. But if I turn this horizontal, and then something else happens. See? If I turn this horizontal like this, I need more force. The reason why, the distribution of the mass, or the moment of inertia, is distributed away from the axis of rotation. Well, of course, the longer this arm is, the more force I need to have angular acceleration or cause torque on this. So now you can tell it's 12 inches on each side, and it's exactly the same mass, but this time has more moment of inertia. See how much force I need? I need more force to accelerate this. See, I need real more force. But see, when I let this go, due to the moment of inertia, if I had a disc like this, it would go for 10 minutes. You can tell. But if it's the other way, there's no way. It's not going to have this much moment of inertia. But see? See, that can go up to 500 RPM. But there's no way I can do the other way. It's just because of moment of inertia. This is another experiment for conservation of angular momentum. Well, what I did this time, this is 8 feet, 516 rod, and it's 740 grams. So is this one, but this is only 2 inches, and this is 8 feet. This will rotate only for 3 minutes, and that's as far as it can rotate. But this rod rotated 12 hours, and then I had no choice to stop it because I had to bring my car in. And I'm assuming it would even go 24 hours because my ceiling is only 8 feet. If I have 16 or imagine like 160 feet, it might even rotate for a week or even 2 weeks or a month. And technically we can call this perpetual motion. So now I'm going to suspend this 740 grams. You can see how fast this rotates. And as I explained, the reason why this one is different because it doesn't have moment of inertia, but this one does. So this one, the moment of inertia is more, and then this one, the rotational speed is more. The reason why it's contracted, or in other words, is toward the center of the axis of the rotation. So I let this go, you can tell how fast this will rotate. And like I said, that goes maximum 3 minutes. And this one, the first rotation takes 4 minutes. But of course I have to be so careful to adjust this. You see, this is also caused by Earth's differential forces, and you can tell how wide this is or how much this is spread from the axis of rotation. Well, of course, there's no doubt after the first rotation it picks up speed or the angular acceleration, and I checked after like 10 hours it was going still. It would take 70 seconds for one rotation, and after that 12 hours the same speed, the same rate happened. You can tell how slow that goes. Even that 740 grams, due to the mass, it will never reach 1000 RPM on likewise small steel balls, but I would say maximum maybe 800. So I'm going to stop this now. You can tell this is going clockwise now. Well, of course, if you pay close attention, you can tell after it overcomes the moment of inertia and it picks up a speed. Well, of course, there is no way you can tell by the center, but you can tell by the tips it picks up a speed because it's too long. I mean, our perception is a little bit different. But if this were like 16 or 20 feet, it would take maybe 2 minutes or 3 minutes for one rotation. Albert Einstein said once, in space, gravitational mass and inertial masses are indistinguishable. So I was always wondering, how could I bring this in my science lab? And finally I found the address. So this is a special pendulum, and then you can tell this is an extension spring, and then I thought if I convert the Hooke's law, like an ordinary pendulum is like this, has a ball, and then goes back and forth. Of course you can do so many things, but what I did on top of this wire, I'll put this extension, and it's exactly 5 inches, but when I put the 1 kilogram over here, it will be extended exactly 14.5 inches. I thought if I get this high enough so I can get the gravitational potential energy, by the time it gets to the top, momentarily it has to stop. Well, it might be even a fraction of a second, and then after that continue, and my guess was right. I was so happy so I could bring the Albert Einstein idea in my science lab. In fact, despite the public perception, free fall is not toward the Earth. Even if I throw this upward, exactly the same thing happened. Technically, it's our perception is going up. It's going upward, but technically it's descending. Every second the velocity is due. And then by the time it gets here, I wanted to prove that right there momentarily, it might be less than a fraction of a second. There is no weight. So my guess was right. And then I had this 1 kilogram. See now the spring is fully extended. Let me go up a little bit, you can see it. See, now you can tell the spring is fully extended. But when I get this going, and you can tell, I'll put some plane over there. By the time it gets to the top, see, you see the retraction right there? See? It's exactly going back to, it seems that at that moment there is no weight whatsoever, and the 1 kilogram has only the inertial mass. Well, of course, this is very complicated mechanics. It's called Hamiltonian Mechanics. And then, when it's up here, I have gravitational potential energy. By the time it gets to the center, gravitational potential energy is almost zero. But at the same time, it picks up the kinetic energy. And then when it goes up again, it's exactly the opposite. It's just conversion of kinetic energy to gravitational potential and back and forth. But you can tell how much it's retracting. It's exactly 5 inches. This is my last experiment for the conservation of angular momentum. And this rod is exactly 8 feet and it weighs 740 grams. But this time I didn't use a string or thread.